Welcome to another physics tutorial program. And today, what I want to talk about is electricity again, but I want to go into the business of voltage and current. We're all familiar with volts. We're not so familiar with amps, voltage and current. And I've decided to begin here, just beside a lovely old Chawton surrounded by prayer flags. And why have I begun here? Well, I suppose you could say that on the one hand, Chawton represents spiritual energy, but just here there is something which represents electrical energy too. So let's walk a little around the Chawton and see what we find. So now, I hope you can see why I've chosen to begin a talk about electricity here beside this old Chawton. Because if we look just here, we see something which is not like a Chawton at all. This is a manifestation of modern Bhutan. This is the electricity distribution centre, which takes power in from Chukka hydropower station and then feeds it out to Thimphu and Wangdi Phodrang. What is all this? And let's go inside and have a look. And let's then start to talk about this word voltage and volts. So come with me down into the Simtoka electricity distribution point. So, here's Mr. Sonam Tobgay to meet us. And Sonam, you're the manager of the Simtoka distribution centre.
Yes.
And that's a really responsible job, isn't it? Because if your distribution station here broke down, if you didn't do your job properly, we would lose all electricity in the whole of Thimphu.
Yes.
And then we'd all be blaming you.
Yes.
Tell me, Sonam, what was your background? How did you come to have this responsible job?
After doing my class 10 at Motithang High School, I went to Dewathang to do my diploma in engineering, the Royal Bhutan Polytechnic.
So you did a diploma in electrical engineering, and then?
Then after that, I passed out in the year 1994. So directly I've been stationed here.
Right.
I was engaged here during the testing commissioning
Right.
In the beginning itself.
Right.
So I was here till now. It has been almost 19 years I've been working in this substation.
Right.
And presently I'm looking after the operation maintenance manager
Yes.
in this substation.
Very good. So, as I say, if you didn't do your job properly,
Yeah.
all the electricity in Thimphu will suddenly stop.
Yes.
No rice cookers, no lights, no television,
Yeah.
no radio. We'd have a real problem.
Yes.
So you've got a pretty responsible job there.
Yes.
What's typical of the sort of problem that might knock this station out?
The problem usually arises during lightning strokes. So during the
Right.
lightning strokes, since the source of the line is quite a lengthy line
Yes.
from Chukka to Simtoka.
How long is it from Chukka to Simtoka?
It's 54 kilometers.
54 kilometers.
Yeah.
Right.
So during a lightning strikes, so on a transmission line, so that the high voltage directly enters the substation.
Right.
In that case, there is a chances of interrupting the whole substation.
Right, right. So remember, if you're watching a really good film on the television and there is lightning going on outside, don't be surprised if your television goes off. In fact, always unplug your television during a really bad lightning storm, because the lightning can strike the lines, the power lines going into your house, cause a massive surge and blow up your television. So you need to be careful in lightning, especially here. Well, now, what actually happens in an electricity distribution station? And this is where I now get on to the topic of this little program, which is about voltage and current. I'm going to explain to you the job of this distribution centre, and for that I'll need a whiteboard. I want to talk about all these units we have for measuring electricity. I'm going to begin by drawing a wire, a simple wire, and down the wire I've got an electric current flowing. So what is an electric current? Well, you've learned that an electric current consists of the flow of electrons in a wire. And you will have learned that electrons have something called charge, negative charge on electrons and positive charge on protons, but it is simply an electrical property of electrons and protons. So let's just think of it as electric charge on the electrons. The electrons are flowing down the wire. Then we come to how we measure electric charge. If you measure things, you have to have a unit to measure them in. If you're going to measure distance, you have to talk about meters or kilometers. If you're going to measure amount of rice, you have to talk about kilograms of rice. So, measuring electric charge, we have to have a unit to measure it in, and that is called a coulomb. And in 1 coulomb, you have got a package, a parcel of charge. How much charge? Well, you've got approximately 6.2 by 10 to the power of 18 electrons. Now, if you write 6.2 times 10 to the power of 18 and then say it in language, you get a very, very large number. Just as 12 eggs make a dozen eggs, so 6.2 times 10 to the 18 electrons make 1 coulomb of charge. 6.2 times 10 to the 18, that's a big number, and I've managed to now write it down. 6.2. Now, if it's times 10 to the 18, I take the decimal point and I move it to the right 18 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And the decimal point ends up there. Let's try saying it. Let's divide it into millions. 1, 2, 3, 1 million. 1, 2, 3 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 million. Well, wow. I wonder if you can say this number. Million, 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 million. So that's approximately 6 million, 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 million electrons in 1 coulomb of charge. Think of all those electrons flowing down the wire. It's a very, very large number. But if I were to take that number of electrons and put them in a little box, then in that box I will have 1 coulomb of electric charge. Now, there's my little box with a coulomb of electric charge in, flowing down the wire. Well, I don't just get one box, I get a whole sequence of boxes flowing down the wire, each one being 1 coulomb. And if I station a person here who watches there with a little stopwatch, and he counts how many of these boxes are going past every second, there they are, flowing past. Somebody says, go, they go past, 1, 2, 3, 4, 5, 6, counts how many boxes of electric charge are flowing past in a second, in 1 second. That is called amps. 1 amp is a flow of electric charge of 1 coulomb per second. If the little man here counted 1 second, go, go, and during that time 1 box went by, the current in that wire would be 1 amp. An amp means a coulomb per second. Let's say 10 boxes were going past in a second. Go, stop. 10 boxes went past. That would be 10 coulombs per second. A coulomb per second is called an amp, so that would be a current of 10 amps. So think of these boxes of electrons. Each box contains those many electrons, and each box is flowing down the wire, and you're counting how many boxes are going past in 1 second, and that is the current. 1 amp means 1 coulomb per second flow down the wire. So why don't we just say 1 coulomb per second? Why do we have another word, amp? Well, when people started to learn about electricity, there were some scientists who made big contributions to our understanding. And one of them was a Frenchman called Henri Ampère. And so to honor him, we have called 1 coulomb per second an ampere, which is shortened to amp. Now, if you find it difficult to think of these invisible boxes going down a wire and you can't see anything moving down the wire, so what's happening, it's often very difficult to imagine what's happening in electricity. Think about this. I've drawn a road here, and I've drawn 2 trucks going down the road. Now, unfortunately, my producer says they look like frogs. I don't think they look like frogs. I think these look like trucks. And in the back of each truck, you might have stones. So here are trucks with stones going down the road. Each truck might have 2 tons of stones on it. 2 tons on each truck. Here's my little man here with the stopwatch. And he's counting the trucks as they go down the road. When 1 truck goes by, that's 2 tons of stones gone. if he counts and there are 2 trucks going in 1 second, that's 2 trucks per second. Just as with my Coulomb boxes of charge, if 2 go past in 1 second, that's 2 coulombs per second, which we call 2 amps. The trucks going past, 2 trucks a second, I could say 2 frogs, if you like. 2 trucks a second, 20 trucks going past in 1 second. You can imagine they'd all have to be going much quicker. 20 trucks, that would be 20 trucks a second. We could have 20 coulombs a second going there. We'd have a current of 20 amps. In your electric kettle or your electric heater, that would typically take a current of about 10 amps, which means 10 of these Coulomb boxes going down the wire through your heater and back out every second. If you have an electric light bulb, it might only be 1/4 of an amp, which would mean not 2, but just 1/4 of a box going through the wire. And if we look at things like computers and microelectronics, we might only have 1,000th of a Coulomb going through the wires, a milliamp. So the amount of current that we get in our use of electricity, the number of coulombs a second that go through the wires, varies an enormous amount, from dozens of coulombs a second, 20, even 30 coulombs a second, down to even thousandths of a Coulomb a second in electronic equipment. And we have to choose wires, and we have to choose components that will carry the amount of current that's going to go through them. So if you think about 3-pin plugs, some 3-pin plugs have got great big, thick brass pins on them, some only thin. It all depends on the amount of current we're going to push through them. Because if the wire's too thin for the amount of current, the wire will heat up and cause an electrical fire. And that's one reason why you get frequent electrical fires in Bhutan, because people do not understand about current, and they will use a thin wire to connect an electric fire, and too much current goes through that wire, causing it to get red hot. And what happens? Your house burns down. So you have to choose the connecting wires in your house according to the current of the devices that you're going to use. Well, let's say each truck carries 2 tons of stone. When 1 truck goes past you, that's 2 tons of stone gone. If 2 trucks go past, that's 4 tons of stone which has gone by. If you wanted to know how many stones you've got, you'd say, how many trucks a second? How many tons of stone on each truck? 20 trucks in a second would give you 40 tons of stone. 2 multiplied by 20. 3 trucks a second would give you 6 tons of stone. 3 trucks a second multiplied by 2 tons of stone. And this brings us now to volts multiplied by amps gives watts. Let me draw my road with the 2 trucks on again. You know they're trucks because they've got wheels on the bottom. 2 tons of stone. 2 tons of stone. Little person here counting the trucks as they go past, and he's got a stopwatch. He counts how many trucks a second go past. Trucks per second. And he measures how many tons of stone on each truck. 2 tons of stone per truck. For example, 3 trucks per second each one carrying 2 tons per truck. 3 trucks in 1 second, each one carries 2 tons of stone. In 1 second, how many tons of stone have I got? Answer, 3 trucks, 2 tons on each truck. Answer, 3 times 2 equals 6 tons of stone. In a similar way, trucks per second. I'm going to change some words now. Instead of trucks, I'm going to put in, so instead of 3 trucks a second, I'll say 3 coulombs per second. Coulombs, remember, measures electric charge. In other words, how many electrons. 2 tons of stone per truck. Well, now, electricity brings us energy. These coulombs, these little boxes I had, they don't carry stones, they carry energy. And what do we measure energy in? We measure energy in a unit called a joule. It's a way of measuring how much energy I've got. So instead of tons, let's say joules of energy. And instead of stones, it's energy. And instead of per truck, it's per coulomb. If I want to know how many joules of energy I've got, if 3 coulombs of electrical charge are going past every second, and each one carries 2 joules of energy, if each coulomb has got 2 joules of energy on it, just like the trucks had 2 tons of stone, the coulomb has got 2 joules of energy on it that it's carrying down the wire. And if 3 of these coulombs go past me in 1 second, then the total number of joules I'll get is 3 multiplied by 2, just as if it was trucks of stone. 3 trucks a second, 2 tons of stone per truck will give me 6 tons in 1 second. Here, 3 coulombs of charge a second, a bit like the truck, moving down the wire, carrying energy. 2 joules per coulomb, 2 joules of energy on 1 coulomb, 1 truck. What I'll get in 1 second is 3 times 2 equals 6 joules, which you notice is coulombs per second multiplied by joules per coulomb gives me joules per second. Now, a coulomb per second is called 1 amp. A joule per coulomb is called 1 volt. So we've got here amps multiplied by volts, or volts multiplied by amps. A joule per second, you will have learned, is a measure of power, energy per second, and that is given the name watts, a watt. So we have the simple little deduction, thinking about our trucks carrying stones, we have the simple deduction, amps multiplied by volts gives us watts, or coulombs per second multiplied by joules per coulomb gives us joules per second. We have, as I mentioned, these words amp, volt, and watts because people wanted to honor the scientists who worked out all about electricity. Instead of a coulomb per second, years ago somebody said, well, let's honor Henri Ampère, who discovered various discoveries on electricity, so let's call that an ampere. Well, that's shortened to amp. Joules per coulomb. Can we think of another scientist to name that after? So, yes, what about an Italian called Volta? And I think I mentioned in a previous program, Volta used to detect electricity by connecting 2 wires to frogs' legs and noticed that the frogs' legs twitched when electricity went through it. So the volt is named after the Italian Volta. You have to be a bit careful here. There was also a French philosopher and poet called Voltaire. Don't mix up Voltaire, the Italian, who was a scientist, and Voltaire, the French poet, writer, and philosopher. Now we come to joules per second. Can we think of a scientist to honour with joules per second? Well, yes. There was a man called James Watt. And James Watt, he was one of the discoverers of the steam engine. And he made a great contribution to the study of energy. So a joule per second was given the name a watt. So that's how we get amps, volts, and watts. And this is how we get amps multiplied by volts gives us watts. Or, to put it the other way round, volts times amps equals watts.